Greetings, this is Terence speaking, and with me, I have Samuel and Ting-Yong. Our research question is, do young adults in their 30s have a higher mean heart rate as compared to middle-aged adults in their 50s? The independent variable, or IV, is age group. The two selected age groups are the 30s age group, including people of age 30 to 39, and the 50s age group, including people of age 50 to 59 years old. The dependent variable, or DV, is heart rate. The reason for choosing this particular IV-DV pairing is because we wanted to find out if young adults have an overall higher mean heart rate as compared to middle-aged adults. In other words, we wanted to study if age group plays any part or role in the heart rate of individuals. The two levels of IV are interesting to study because studying whether independent variable, age group, has an effect on the dependent variable, heart rate, may provide an insight to scientists on why certain diseases only occur in middle-aged adults rather than young adults or vice versa. We selected a higher mean heart rate as a form of comparison because we are only interested if young adults do actually have a higher heart rate than middle-aged adults. Studies were done and they showed that the maximum heart rate has a slight but steady decrease of about 1 beat per year starting from the age of 10 to 15 years old. Therefore, individuals who are younger should have a much higher heart rate than those who are older, which is why we chose our research question. This is the summary statistics of the heart rate of young adults in their 30s. While this is the summary statistics of heart rate of middle-aged adults in their 50s. Here's the histogram of heart rate of young adults in their 30s. And this is the histogram of heart rate of middle-aged adults in their 50s. This is a box plot comparing the heart rate of young adults in their 30s and middle-aged adults in their 50s. By comparing the box plot of heart rate of young adults in their 30s with the box plot of heart rate of middle-aged adults in their 50s, and looking at the whiskers on the box plot, it is evident that the spread of data of heart rate of middle-aged adults in their 50s is much greater than the heart rate of young adults in their 30s. From the box plot, it can also be observed that the interquartile range of heart rate of middle-aged adults in their 50s is much higher than the interquartile range of the heart rate of young adults in their 30s. This means that the heart rate of young adults in their 30s are relatively close to one another, giving rise to smaller dispersion. However, all the heart rates of middle-aged adults in their 50s are relatively far apart from one another, giving rise to a wider dispersion. The median should only be used if the shape of the distribution is skewed, and there are outliers, since both distributions of both groups are symmetrical, with one group having outliers while the other not having any outliers. Median is not a good way of comparing the central tendencies of both the datasets. However, mean will always be a good way to compare both datasets, since mean is used when the shape of the distribution is symmetrical and there are no outliers. However, the sample data for young adults in their 30s contain outliers. The mean will still be a relatively good comparison of the central tendencies between the two datasets. Since our question is, do young adults in their 30s have a higher mean heart rate as compared to middle-aged adults in their 50s? Our intermediate conclusion is that young adults in their 30s do not have a higher mean heart rate as compared to middle-aged adults in their 50s. The dispersion of young adults in their 30s is also lower than that of middle-aged adults in their 50s, and the distribution of the heart rate of young adults in their 30s is less symmetrical and much more normal as compared to the middle-aged adults in their 50s. However, in order to make a better conclusion, we will have to check this descriptive and statistical analysis conclusion with hypothesis testing, which will be discussed. I've come to the end of my segment. The next section on inferential statistics will be presented by Ting-Yong.
Before we calculate the inferential statistic, let me explain what is type 1 and type 2 error. Type 1 error means that null hypothesis is true, but we rejected null hypothesis. The possible consequence is that the middle-aged adults might become more worried about their health as they believe that increasing age will cause a decrease in heart rate. This may lead to a psychological consequence which may in turn cause heart-related diseases. Type 2 error is that HA is true, but we do not reject null hypothesis. The possible consequence is that this might give an impression that there is indeed no difference in heart rate for middle-aged adults. Thus, they might dismiss any risk of getting heart-related diseases and might even skip regular checkups, thus giving them a false sense of security. Influential statistics was calculated manually and Minitab was used to support our answer. As mentioned earlier, we are interested to find out if the mean heart rate of young adults in their 30s is higher than the mean heart rate of middle-aged adults in their 50s. Thus, null hypothesis is where mu1 is equal to mu2, and HA is where mu1 is greater than mu2, where mu1 is the mean heart rate of young adults in their 30s, and mu2 is the heart rate of middle-aged adults in their 50s. Since we are sure that young adults have a higher heart rate than middle-aged adults, we need to make it harder to prove that HA is correct. Hence, the level of significance should be smaller so that a higher confidence level will result. Therefore, we have decided to use 5% level of significance as compared to 1% or even 10% level of significance. If the level of significance is too high, the probability of committing a type 1 error will be higher. If the level of significance is too low, the probability of committing a type 2 error will be higher, and the confidence interval will be much greater, and therefore harder to reject the null hypothesis. To accurately compare both statistics of both age groups, F-test was first conducted at 5% level of significance to determine if both variants are equal. F-test is a two-tailed test. The null hypothesis H0 is where variance 1 is equal to variance 2. The alternative hypothesis HA is where variance 1 is not equal to variance 2. In this case, variance 1 is the variance of young adults in their 30s, and variance 2 is the variance of middle-aged adults in their 50s. The level of significance is 5%. Therefore, confidence interval is 95%. Lower critical value is 0.57. Upper critical value is 1.76. The F-test statistic is 0.50 and the p-value is 0.0018. This is our F-statistic data from Minitab. This is our two-tailed F distribution plot showing the critical region. If H0 fall within the critical region, it is rejected. Therefore, since Fs is smaller than lower critical value and the p-value is smaller than the level of significance, H0 is rejected. The test is significant. This means that variance 1 is not equal to variance 2. Now I will pass on to Samuel, which will continue the two independent t-tests.
Since we are only interested in whether young adults in their 30s have a higher mean heart rate as compared to middle-aged adults in their 50s, a right-tailed two independent t-test was used. Thus, degree of freedom is equals to 88 and effect size is equals to 0.33. The standard error is equals to 2.62. Test statistics is equals to negative 1.21 and the margin of error is equals to 4.36. This is our right-tailed t distribution showing the critical regions. If H0 falls within the critical region, H0 is rejected. Therefore, since the test statistics is not within the critical regions and p-value is greater than the level of significance, H0 is not rejected. This means that the mean heart rate of young adults in their 30s is the same as mean heart rate of middle-aged adults in their 50s. The 95% lower bound confidence interval was constructed, and the p-value is equals to 0.886. Since p-value is greater than the level of significance, H0 is not rejected. Therefore, both means of 30s and 50s age group are the same. This is our two sample t statistics data from Minitab. This is our diagnostic report on the power of our test. The power of our test is 50.2%, which may not be powerful enough to reject our H0. Our desired power is 90%. Therefore, we should increase both sample sizes so that power will be increased as well. In order to achieve 90% power, both sample sizes have to be at least 156 as compared to our current sample size of 50. This is quite a significant difference as the desired sample size is almost 3 times our current sample size. In conclusion, H0 is not rejected. This means that the means are the same. Although the means of young adults in their 30s is similar to middle-aged adults in their 50s, there could be extraneous variables involved that we were unable to control. For example, possible extraneous variables would be whether individuals exercise, whether they have heart diseases, their diet, whether individuals are at rest, their weight, and their metabolism rate. Thus, we should take into consideration all these extraneous variables before the commencement of the study. We have come to the end of our video. Thank you for your kind attention.